Hello guys, myself Vasundhara and today I am going to explain about demultiplexer problem concept, and the contents of this topic are introduction to demultiplexer, types of demultiplexer, then problems on different types of demultiplexer, advantages of demultiplexer and conclusion. Then first, introduction to demultiplexer. A demultiplexer, often abbreviated as DMUX, is a digital circuit used in electronics and telecommunications to route data from one input to multiple outputs. The demultiplexer performs the opposite function of a multiplexer, which takes multiple inputs and select one output, whereas the demultiplexer takes one input and selects one of the several outputs. Then the purpose of a demultiplexer is demultiplexer are primarily used to distribute data or signals from a single input to multiple outputs. They are commonly employed in digital communication systems, memory addressing, and data routing applications. Functionality. A demultiplexer has one input line and several output lines. The input data or signal is directed to one of the output lines based on the control inputs. The control inputs determine which output line will receive the input signals. Symbols. In circuit diagrams, a demultiplexer is represented by a rectangular block with one input line, several output lines, control input lines to select the desired output. Implementation. Demultiplexers can be implemented using various digital logical components such as AND gates, NOT gates, and multiplexers. Truth table. Demultiplexers have a truth table that illustrates the relationship between control input, and output. This truth table helps in understanding the behavior of the demultiplexer under different input conditions. Types of demultiplexer. 1:2 demultiplexer. This type of demultiplexer has one input and two output lines. It selects one of the two output lines based on the control input. 1:4 demultiplexer. With one input and four output lines, this demultiplexer selects one of the four output lines based on the control inputs. 1:8 demultiplexer. A demultiplexer with one input and 8 output lines. It selects one of the 8 output lines based on the control inputs. 1:16 demultiplexer. This demultiplexer is a digital circuit that takes a single input signal and routes it to one of the 16 possible output lines based on the control signal provided. 2:4 demultiplexer. This demultiplexer takes two inputs and selects one of the four output lines based on the control input. 4:16 demultiplexer. With 4 input lines and 16 output lines, this demultiplexer selects one of the 16 output lines based on the control inputs. Let us see in detail about 1:2 demultiplexer. In the 1:2 demultiplexer, there are only two outputs. We have given it as Y0 and Y1. One selection line, that is S0, and a single input, that is A. On the basis of the selection value, the input will be connected to one of the outputs. The block diagram and the truth table of 1:2 demultiplexer are given below. So we can see the demultiplexer. Here we have given as input as A, and here is a select line. Then here are the outputs, and this E is nothing but enable. This is the truth table for 1:2 demultiplexer. Then here the selection inputs are taken as a selection line and outputs are Y1 and Y0. When we give the input as 0, we'll get the output Y1 as 0 and Y0 as A. Then when we give the input as 1, we'll get the output as A and 0. For Y1 will be get A, and for Y0 we'll get 0. Then the logical expression is Y0 is equal to S0 bar A. Then Y1 is equal to S0 into A. Next, this is a logical circuit for the above expression. That is, here we use one NOT gate and two AND gate, and as it is, we'll get one input and two outputs. So Y0 and Y1 are the outputs. Here we are using the NOT gate and two AND gates. Here S is nothing but the selection line and A is the input. Y0 and Y1 are the outputs. Next is 1:4 demultiplexer. In 1:4 demultiplexer, there are total of 4 outputs, that is Y0, Y1, Y2 and Y3, 2 selection lines, that is S0 and S1, and a single input, that is A. On the basis of the combination of inputs which are present at the selection lines S0 and S1, the inputs will be connected to one of the outputs. The block diagram of 1:4 demultiplexer is here A is the input, and we are using in 1:4 demultiplexer we are using 2 selection lines, that are S0 and S1. Then we are, as it is 1:4 demultiplexer, so we are getting 4 outputs, Y0, Y1, Y2 and Y3. Now we are gonna see the truth table of 1:4 demultiplexer. Here the input is nothing but the select lines S1 and S0, and the outputs are Y1, Y2, Y3, Y and Y0. Here when we give input as 0 and 0, we'll get at Y0 as A. Then when we give 0 and 1, we'll get Y1 as A. And when we give 1 and 0, we'll get Y2 as A. And when we give 1 and 1, we'll get Y3 as A. Then the logical expressions are for Y0. As in Y0 we are getting the output, so Y0 will get S1 bar, S0 bar and A. Like Y1 is equal to S1 bar, S0 A. Y2 is equal to S1 S0 bar A, and Y3 is equal to S1 S0 A. So now we are gonna see the logical circuit of the 1:4 demultiplexer. Here we are using 2 NOT gates and 4 AND gates. First, here A is nothing but the input lines, and S1 and S2 are the select lines. Here Y0, Y1, Y2, Y3 and Y4 are the outputs. As in demultiplexer, it is one input, many output, so we are getting here 4 outputs, where here we are using 4 AND gates. Next, we'll go to 1:8 demultiplexer. In 1:8 demultiplexer, there are total of 8 outputs. That's Y0, Y1, Y2, Y3, Y4, Y5, Y6 and Y7. 3 selection lines, that are S0, S1, S2, and a single output Y, A. On the basis of the combination of inputs which are present at the selection lines S0, S1 and S2, the input will be connected to one of these outputs. The block diagram is here A is the input, and all Y0 to Y7, these are all the outputs, and here we have 3 selection lines. Next, the truth table is here we are having 3-bit, like 3-bit, as it is 3 selection lines. So when we take the inputs as 0, 0, 0, we'll get Y0 as A. When we take 0, 0, 1, we'll get output at A as at Y1. Then when we take 0, 1, 0, the output will be at Y2. Then when we take 0, 1, 1, it is the A is at Y3. Then when we take 1, 0, 0, the output is at Y4. Then when we take 1, 0, 1, it is at Y5. Then when we take 1, 1, 0, it is at Y6. And at last, when we take all the 3 as 1, 1, 1, which is all the 3 are high, we will get the output at Y7. So the logical expression of the 1:8 demultiplexer is, we'll get Y0 is equal to S0 bar, S1 bar, S2 bar, A. Then for Y1 we'll get S0, S1 bar, S2 bar, A. Then for Y2 we'll get S0 bar, S1, S2 bar, A. And for Y3 we'll get S0, S1, S2 bar, A. For Y4 we'll get S0 bar, S1 bar, S2A. For Y5 we'll get S0, S1 bar, S2A. For Y6 we'll get S0 bar, S1, S2 and A. For Y7 we'll get S0 bar, S0, S1, S3 and A. So next, so logical circuit for 1:8 demultiplexer is, here the input is A and there are 3 selection lines, that is S0, S1, S2, and outputs Y0 to Y7 are the outputs. Here we are using 3 NOT gates and 7 AND gates. Okay, next 1 is to 16 demultiplexer. In 1 is to 16 demultiplexer, there are total of 16 outputs from like Y0 to Y16, then 4 selection lines S0, S1, S2 and S3 and and a single input, that is A. On the basis of the combination of inputs which are present at the selection line S0, S1 and S2, the input will be connected to one of these outputs. The block diagram is, here we are taking A as the input and we are used from Y0 to Y15 are the outputs, and there are 4 selection lines, that is S0, S1, S2 and S3. Now we can see the truth table of 1 is to 16 demultiplexer. The inputs are the selection lines S1, S2, S3 and S0. Outputs are Y0 to Y15. When we give all the inputs as low, we'll get at Y0 as A. When we give S0 at S0 as 1 and all the other as low, we'll get Y1 as A. Then when we give for S1 1 and all the other low, we'll get Y2 as A. In the same way, and it will continue till when everything is high, we'll get at Y15 as A. So next, the logical expression of the 1 is to 16 demultiplexer is Y0 is equal, for Y0 will get A bar, S0 bar, S1 bar, S2 bar, S3 bar. Y1 is equal to A into S0 bar, S1 bar, S2 bar and S3. Y2 is equal to A into S0 bar, S1 bar, S2, S3 bar. Y3 is equal to A into S0 bar, S1 bar, S2, S3. Y4 is equal to A into S0 bar, S1, S2 bar, S3 bar. Y5 is equal to A into S0 bar, S1, S2 bar, S3. Y6 is equal to A into S01, S1, S2 and S3 bar. Y7 is equal to A into S0 bar, S1, S2, S3. Y8 is equal to A into S0, S1 bar, S2 bar, S3 bar. Y9 is equal to A into S0, S1 bar, S2 bar, S3. Y10 is equal to A into S0, S1 bar, S2, S3 bar. Y11 is equal to A into S0, S1 bar, S2, S3. Y12 is equal to A into S0, S1, S2 bar, S3 bar. Y13 is equal to A into S0, S1, S2 bar, S3. Y14 is equal to A into S0, S1, S2, S3 bar. Y15 is equal to A into S0, S1, S2 bar, S3. The logical circuit for the 1 is to 16 demultiplexer is, we are using A as the here A is the input and S0 to S3 are the selection lines. Even we use this as the inputs, and from Y0 to Y15 these are the output lines, and here we are using 4 NOT gates and 16 AND gates. Problems on demultiplexer. Creating 1 is to 8 demultiplexer using 1 is to 4 demultiplexer and 1 is to 2 demultiplexer. Here we can implement the 1 is to 8 demultiplexer using lower order demultiplexer. That is, we can create a 1 is to 8 demultiplexer using 1 is to 4 demultiplexer and 1 is to 2 demultiplexer. Here we will use 1 is to 4 demultiplexer, 2 selection lines and 4 outputs and 1 input. In 1 is to 2 demultiplexer, which has only 1 selection line, for getting 8 data outputs, we need 2 1 is to 4 demultiplexer and 1 is to 2 demultiplexer. So in order to get the final output, we have to pass outputs of 1 is to 2 demultiplexer as an input of both 1 is to 4 demultiplexer. Next, the block diagram of the 1 is creating 1 is to 8 demultiplexer using 1 is to 4 demultiplexer and 1 is to 2. Here we use 2 1 is to 4 demultiplexer and 1 is to 2 demultiplexer. So here A is the input and we are using 1 S to this selection line, as we'll get 2 outputs. So we will take the one output as connected to 1 is to 4 demultiplexer. Another output is connected to 1 is to another 1 is to 4 demultiplexer. Here we have two selection lines S1 and S0, and we'll get here we'll get at the first 1:4 demultiplexer 4 outputs, and at the second 1:4 demultiplexer we'll get the 4 outputs. So here it's like 8 outputs. It is 1:8 demultiplexer. Next, creating a 1:16 demultiplexer using 1:8 and 1:2 demultiplexer. We can implement the 1:16 demultiplexer using a lower order demultiplexer. To implement 1:16 demultiplexer, we need two 1:8 demultiplexer and one 1:2 demultiplexer. The 1:8 demultiplexer have 3 selection lines, 1 input and 8 outputs, and 1:2 demultiplexer has only 1 selection line. For getting 16 outputs, we need two 1:8 demultiplexer. The 1:8 demultiplexer produces 8 outputs. So in order to get the final output, we need 1:2 demultiplexer. So the block diagram of 1:16 demultiplexer, creating a 1:16 demultiplexer using 1:2 and 1:8. Here we'll use 1:2 demultiplexer and two 1:8 demultiplexer. Here A is the input and S1 is the selection line. Here we have three selection lines, S0, S1, S2, and here we'll get 8 inputs, 8 outputs, and here also we'll get 8 outputs. We can also solve the problems of demultiplexers using the Verilog programs. So here is one example of such Verilog program. First, in Verilog we'll use module and end module. So in the module, first we are giving the name of we are using the example of 1:4 demultiplexer. So we are doing demux 1:4. The input is taken as D, as we have two select lines, so we are giving a 1:0. Then at output we are having 4 outputs, so 3:0. Then we at the cases it is a 3 bit, so we'll take 3 B00. It is nothing but the outputs, like when we get 0 and 0, what is the output, and at 0 and 1, 1 0 and 1 1. Next, here we'll end module. Next, we are using the test benches. In test benches, the inputs are taken as REG. So here the input D is taken as REG D. Then the select lines are also, it is in REG. Then the output is here the output is taken as wired. Then here the hashtag 100 is nothing but the time frame. So here is this one exam output for the 1:4 demultiplexer in Verilog. The advantages of the demultiplexers are, by using the demultiplexers we can increase the efficiency of the communication system. Then demultiplexers can separate different signals from a mixed signal stream. Demultiplexers can decode the signals produced by a multiplexer. Demultiplexers are used in several input and output devices for data routing. Demultiplexers are used in digital control systems to select one signal from a mutual stream of signals. Demultiplexers are employed for a data transmission in the secondary systems.